much. Are there actually any Erlang programmers here? None. Oh, that's oh, one, two. Is that all? That's great, because I'm not preaching to the converted. I'm preaching to the unconverted, which is gives me a great opportunity to convert a few of you. So, unfortunately, this monitor in the middle doesn't work. It's because I'm told this is an American Mac and not a British Mac. Apparently, they don't speak the same language. Or perhaps they will if we press the right button there. But something about 50 and 60 hertz, I believe. Yeah, so imagine a sort of fireside chat where you know, the old guys tell how it was in the old days and tell you about the mistakes that we made and things like that. So the format of this lecture is the before, how, and now format. It's a pretty standard. You spend about 5 minutes telling you how it was in the bad old days, and then you spend 40 minutes telling you how you got from being where you were at to today, and then you spend about 5 minutes saying where we are today. And that's the format. Jonas said had to have some title for a lecture. I didn't actually know I'd been doing reactive programming, and then Jonas said, yeah, but you know you've been doing reactive programming for years. So I had to have the word reactive in the title. So stuff I've learned building reactive systems. And I where's Jonas? I can't see him. Was that all right, Jonas? Oh, was it okay, the title? I don't know. And then I said, well, sort of, I thought, I was sitting on the underground, I thought, oh, 6 things I've learned. You know, people like numbered lists. I wrote 6 things I learned building reactive systems. And I started on the underground. I got to Schiester, and I'd written 35. So I thought, so I put in a title that was K things I'd learned, you know, where K is greater than 35, because I thought I'd think of some more things. And then I thought, I can't possibly give a lecture that's got 35 things I've learned, because you just wouldn't remember. So I kind of stripped it down to half a dozen things. So this is the things I think... I tried to make them into sort of little catchphrases so you remember them. So I don't know if you ever read it, but the wisdom of Balthazar Graciani, I don't know how you pronounce his name, Graciani, he was a Spanish guy, and he wrote this practical, what's it called? Practical manual for good and perilous times. So I thought, you know, we live in perilous times. People spy on us. Computers crash. We've totally fucked up computing in the last 40 years, and I'm partially responsible. So I thought I'd just sort of basically it's a catalogue of the mistakes I've made and the process through which I've been. So I've got to start in the before bit. So of course we know that what's the ultimate reactive device. Right, well, I said, well, it's a telephone, actually. So I have a long, you know, this is a picture of a telephone. And when I started this work that led to Erlang, I got a job at Ericsson and had to program a old-fashioned telephone, computer-steered. I mean, the first computer-controlled telephone exchanges come from about 1974 or 1978. They were being steered, and I got a job at Ericsson in I think 1984 or 1985, and wanted to program. I want to find a better way of programming a telephone exchange. Now, a telephone exchange is a sort of ultimate reactive device. Even in 1984, 1985, you've got this thing, and it's got about 50,000 people, 50,000 simultaneous connections going into it, and it's got to make decisions within about a millisecond. So people start dialing, you know, and they lift the phone up, they hear a dial tone, and they start dialing numbers, and you stop the dial tone. So they're described by communicating finite state machines with response times of around about a millisecond to 2 milliseconds. And so we're doing that way back from about 1978. And of course, all these things were connected into a World Wide Web. Before the World Wide Web and before Internet was invented, the telecoms people had built things like number location services, international collaborations with CCITT had standardized all this stuff. And we were building the software to control that. So we did manage to learn something. So I was just looking back and found a patent that some of my colleagues made that just shows the sort of the architecture of things. There's a little state machine on the left. It's communicating things. These little boxes with arrows in, they represent messages. And it's a pure message passing system. They ran at about 50,000 subscribers with, say, max 5,000 connected at one time, doing some signaling. From the computer's point of view, they do very short bursts of computation and they sleep for a very long time. So we built this system we started working on a system like that in the mid-'80s. And by the mid-'90s, I think we were beginning to put that stuff into practice. So this is a patent from 1991, where it certainly was in practice, and it had been made to program telephone exchanges with. And my boss then wrote a paper about this. He did a licentiate thesis and published that 10 years later. He was describing this work, and he had a list of the characteristics of the kind of systems that we were trying to build. And if you compare that with the reactive manifestos list, I think you'll find quite a large overlap. Handling a large number of concurrent activities, that's the concurrency parallel bit. Actions to be performed at a certain point of time, that's the kind of soft real-time bit. Systems distributed over several computers, that's the distributed bit. Interaction with hardware, and so on. Continuous operation over many years. So way back then, we were really talking about building systems that had uptimes, or rather we talked about the downtime, shouldn't have a downtime of more than 4 minutes per year. So we had to pay fines if they were out of service for more than 4 minutes per year. And so from that problem domain, we managed to make a programming language, Erlang, which I was intimately involved with, made the first version, and that has, I've been writing some of these slides this morning because I thought, well, Jonas had mentioned share nothing and immutable. I thought, well, perhaps I should, there's only 2 Erlang programmers here, and the rest of you don't know Erlang, but Erlang is characterized by its share nothing, immutable state, pure asynchronous message passing. Everything is driven by events. It's distributed concurrent soft real time and has dynamic code upgrade. So, yeah, well, I was doing that in 1985, so I thought, hang on, that's 30 years ago. So I'm rather surprised that people are saying it's new, but we never called it reactive. Okay. So my personal involvement with that was to build that thing and to do it, and then I've followed it ever since. Well, apart from when I left and started a company and got fired and various other things happened. So the bit that I've been playing around in the last few years is the mobile telephony bit. So I just take a brief tour through mobile telephony. It's quite fun. It starts in 1956. In 1956, Ericsson made the first mobile telephone. I mean, proud to work for Ericsson. We made the first mobile telephone, and there it was. I mean, it's a beautiful little 40-kilogram thing. It's lovely. Isn't it beautiful? That's the world's first mobile telephone. Unfortunately, it didn't sell very well, and nobody really knows why, because it was fantastic mobile communications. Estate agents would buy it, and they had a truck, and they'd put it in the back, and they could go out and do it. There was a main market with actually estate agents, because they'd drive it around in their trucks. That wasn't very practical. Ericsson made the first NMTA, Nordic Mobile Telephony System A, which was the first practical one. It was like that. So this is a great improvement, because you got a rucksack with it. And that was great. That's fantastic. And then since then, phones have got smaller and smaller and smaller. And so I looked up on the net the world's smallest phone, and this is apparently the world's smallest phone. It cost $75 from eBay, and the British government are thinking of banning it because apparently it's very popular among prisoners. Because it just looks like a key ring, and they've got it in their pocket, and they can make phone calls, so people don't want that. So if we look at the sort of reactivity of these devices, they fall into this I've put them in 3 categories here. Pre-1981, non-reactive at all. They're just no data services at all. Can't do anything useful with them. They're purely analog. And then 91, 92, you've got 2G, the GSM system. That was a digital system. It was 13 kilobits per second, but that was used to encode voice. So there wasn't a data channel. And then there was an SMS, a short message service, which you could just send short messages, a couple of 100 bytes, I think. 2000, we got the first 2.5G systems, GPRS, which was 32 to 40 kilobits per second and a 600 to 700 milliseconds latency. And that was the first system where the backbone of that system was programmed in Erlang, or the Ericsson equipment was. And then in 2001 came 3G, wideband CDMA, max 168 megabits per second downlink, 22 megabits per second uplink. And then 2009, 4G, again, first place in the world to deploy it without in Schiester, where I work at Ericsson. And it's now running at, what does it say there, 300 megabits per second downlink. Notice that shares that between all the number of users. You can get a max of 256 users. If there's 256 users in a cell, they're only going to get, 186 sorry, what am I talking about? 300 megabits divided by 256. They get a megabit each if they're lucky. That figure of 300 megabits is when there's one user, sort of, here's the antenna, and he's just sort of stood in front of it like that. You get irradiated and 300 megabits per second. What are we going to see in the future? 5G. That is, 5G is said to happen in 2020 plus, which means it's so far ahead we can forget about it, but that's going to be 1 to 2 gigabits per second, dense small cells and the Internet of Things, but we're not there yet. The maximum speed I've heard of in the labs is 2 gigabits per second for single antenna. Right. So where did Erlang come into all of this? 2 more pictures and then we'll get onto the lessons. The 3G systems kind of look like this. Does the pointer occur on the screen? No. OK, right. So where's the stick? No stick. OK, so over here, this is called a node B. This is the stuff that sits in the rooftops. OK, so you know those things you see when you walk around town, you see antennas. Well, that's the bit you see. That's sticking out on the roof. And normally under the roof or bolted onto a chimney is that thing there, okay? And it consists of a radio unit, and it talks to an antenna, and it talks to a digital unit. And that's all. That's a supercomputer. It's in the sky, and Ericsson sells, I don't know how many of these things, possibly millions. That's where we make all our money from these things. They connect to something called a radio network controller. A radio network controller talks to another thing, and then it goes out this way. You can imagine that replicated. If you make a phone call, it goes like that, like that, like that, and into another one of those on another rooftop somewhere. If you want to get out to internet, it goes this way through something called an SGSN, which is a serving GPRS support node, and that is where Erlang is. That's where we program all of those, all Ericsson equipment there. This little fella is written in Erlang, and it goes down to a router. So your smart data wouldn't work if you're using Ericsson equipment if Erlang didn't work. And that, the 3G, we've got 40% of the world market in 3G. If you look at the 4G systems, they look like this. We've got rid of the radio network controller, and it talks to an MME directly. So these things, oh, and it's got an E. It was a node B before. Now it's an E node B. E stands for extended. Again, it's a supercomputer in the rooftops. It talks to the other ones, and it talks to an MME. The MME gets you out to internet. The MME is also programmed in Erlang. We have 60% of the world market there. So in rough figures, Erlang is controlling 50% of the world's telecommunications. And the data rates there are far greater than the application layer. If you put the application layers on top, they're not doing anything. We're really signaling like hell down there. So that's kind of cool. So that's where I am and where I've been at. And the thing that Ericsson sells there, this MME and SGS, it looks like that. It's a big rack full of stuff. It supports 18 million users per rack, 100 billion users or something, and it's jolly expensive. And please go and buy them. They're ever so good, ever so lovely things. Right. So that's where I come from, and now I'm going to tell you how we program these things and what we did wrong. Well, as you know, there are 2 schools of thought as to how you should program concurrent application. There's shared memory concurrency, and that's evil, you shouldn't use it. There's message passing concurrency, and that's ever so good, and we understand that. And I think it's kind of easy to see why shared memory concurrency doesn't work. I mean, where do you put the memory when the thing, if you've got one node in America and the other in Australia, where the hell is the memory? Is it in the middle of the Pacific or something? It doesn't exist. It's either in America or it's in Australia. And in order to share it, in this distributed state. You have to break the laws of physics. Well, we don't like breaking the laws of physics, so it's not going to work. But if you've got two memories, you're not breaking any laws of physics. So that's fine. That's how we work. We've all got our own memories, and we use message passing to communicate. So that's fine. So if we're going to have things that are distributed, the only way they can talk to each other is sending messages to each other. And the main problem we're going to raise is how do we connect things together? Because they are in different places. So the first thing I'm going to talk about are the problems involved in connecting things together. Right. So, connecting things, if you don't take care, you can get a complete mess when you connect things together. This is the hardware mess that you get when you connect things together, but there's an equally big software mess you can get when you connect things together, and you can't see it. I don't know. I don't expect you to read this, but I just plucked it off the net. You know, some person squealing in anguish about I'd just learned Backbone.js and it's already out of fashion. Perhaps I should have used Ember.js, and I should have used handlebars or not moustache, or should I have DOM snippets and all. You know, I mean, it's really horrible today. When I learned programming, there were 3 programming languages: Fortran, COBOL, and assembler, and so there wasn't much choice, and you know, you had to wait 15 years for the next programming language. You didn't have all this horrible amount of choice that you have. So when you start connecting things together, we move into a heterogeneous world where things aren't the same. So the first thing we want to think about are how you connect things together. So suppose you want to connect a Ruby program to an Erlang program. Well, at one level of abstraction, you just use APIs. You just make function calls inside Erlang or inside Ruby, and that causes something magic to happen, and some effect takes place inside the other language. But what's inside that red arrow? What's inside the bit that connects the two things together? If you look at that in a bit of detail, you'll see something like this. Usually what happens is there's a badly documented API for a library that exists in Ruby, and a badly documented API for Erlang. And they talk to a communications medium which is totally undocumented. And you have to kind of figure out how to make the bloody thing work. Right. So at that stage, you go, well, this doesn't work. Right. So then you say, well, what do you do about that? Well, you could read the code. Oh dear. Yeah, but suppose it's a language you don't know. You know, I know Erlang. I don't know Ruby. You know, so well, a little bit, but I mean, I'm not any good at it. And if it was written in Java or something, one of these modern languages, I wouldn't have a clue what it was. I mean, it's horrible stuff, and it's terribly verbose, so I couldn't actually figure out what it's doing. So you can either read the code, or you can use Wireshark. Oh dear. Have any of you used Wireshark to figure out how a Oh, good, right, well, that's good. So this is my first lesson, or the first thing I would like you to remember is describe what's on the wire. Right. And I'm glad Peter's sitting here, because the 0MQ stuff actually has a specification in your RFCs, of RFCs 6, 12, and 23, or which are 35. They describe what you see on the wire in AMQP. Sorry, 0MQ. Sorry. Slip of the tongue. No, and it's absolutely amazing, because I sat down there and just, because I know what's on the wire, just write a program, and it's got to stick out these bits, 0, 1, 0, 1, 1, and then send them down the wire, and it all works. You know, it's great. And I don't need to read these goddamn awful APIs. You know, I hate reading code. I can't understand it. Right, so if you ever find you're using Wireshark, that's a total admission of failure. You should not have to use Wireshark to figure out how something's done. Okay, right. So if we expand this idea of what's happening in between processes, we're going to draw the picture like that, not as a little thin arrow, but as a big fat arrow where something interesting is happening. And we're very good at describing what happens in black boxes. These are the things at the end of the wire, but we're not very good at describing what's inside the wire. Okay, so I want to talk about describing what's inside the wire. Now, what's inside the wire is a protocol. It's what I call a protocol, and a protocol is a contract. Okay, it's an agreement between two parties. And what are contracts for? Okay, if you ask a lawyer what a contract is, they will say, a contract is something that is used to assign blame when things go wrong. Because you never use a contract. If everything works, you're never going to look at the contract. It's going and everything works. But when it breaks, you want to know why it is broken. Okay, so contracts are a thing that are used to assign blame. Right. And so, well, that's a start, you see, because when we make software systems today, I want to move from this, that we've got software that doesn't work and we don't know why, to we've got software that doesn't work and we do know why. And the first problem you find in building complex systems is pinning down errors to where the error has actually occurred. If you actually knew which component had failed, you would be able to start debugging that. But at the moment, we don't know which component has failed. We daisy chain 20 or 30 things together and note that the end-to-end behavior is wrong. We don't know which of these 20 things has gone wrong in the middle. Right. So this is kind of funny. If we have a client and a server, and they're connected by a socket, when in principle, and I say only in principle, we should be able to change either the client or the server, leaving the other side alone, put a completely clean room implementation of the other side, and it should just work. But that is extraordinarily difficult because we have not explicitly described what's going on in between them. We've described the APIs to the programming language at either side, but we haven't described what's on the wire. So, I mean, this is crazy. I found a lovely program called Chandler, which I'm a great fan of, and there was a Chandler client written in JavaScript. That was great. And there was a Chandler server written in Python, I think. Yeah, it was okay. And it all worked beautifully. I thought, well, I'll just take the Python server and write an Erlang server, and I can make it sort of scale, because the Python one didn't scale, but the Erlang one did scale. But the protocol wasn't defined. I mean, the APIs were defined. That didn't help. Let's start reading the JavaScript. It's Ajax call, right, embedded in the middle of thousands of lines of stuff. That's what the protocol description was. Horrible. Couldn't use it. So I had to rewrite both the client and the server, which was rather a shame. Whoops, I'm going the wrong way. So you've got a client, and it's described by a state machine, and you've got a server, and it's described by a state machine. But what describes the wire? Okay, so that's where the contract comes in. Here's a contract, and it's describing what's on the wire. And once you've described what's on the wire, you can bung a contract checker in there. Contract checker checks what's going on all the time, like that. So I'm suggesting the client-server architecture isn't very good. It should have a contract checker in the middle. And then you write this contract checker, and it just sits there sort of waiting for a mistake and sort of pounces on it. And that's very nice. So if we had a contract checker, that would be great. And then so the next question you'd have to ask is, so how do we describe the contracts? Well, yeah, that's interesting. How do we describe contracts? Quite often contracts are described in APIs, just like rote procedure calls, but that's not a good idea, because APIs are APIs are broken. It's a silly idea. Here's a sort of API. This is actually an Erlang. You read it like this. I stood over there last time. Stand over here this time. I saw the Rolling Stones. Mick Jagger sort of ran alternatively from left to right of the stage. I thought that's a good thing to do. So this is a specification. So if you open a file in a mode, you get a handle back, or you get an error for some reason. And then if you close the file, you give it the handle, and it says, yeah, okay. Yeah. And then you can do things on it. You can read from the handle, that's a read from that handle 14 bytes, and you'll get the data. So that looks pretty much like the API in any programming language. It looks like that in Erlang. It looks different in Java or C or something like that. That's pretty useless, actually, because it doesn't tell you that a program like this is incorrect. Open the file, close it, and then read it. Excuse me. APIs, you can type check the bloody thing, but it doesn't tell you that program's wrong. When it's a protocol, it gets even worse because you've got all this stuff going on. So you need to augment that a little bit. It's quite easy to augment it by adding a state. So if we add an additional state to that, if we say, okay, we can only open a file when this is describing the line in between. We can only open it when it's in a state start. And if we manage to open it it'll get you into a state ready, and when we close it and it's ready, it's going to move to state closed, and if it's ready, we can read it, and after we've read it, it'll be in state ready. And then we can type check the code if we want to. We can statically type check it. But I wouldn't like to statically check it. I'd like to put that type specification into the contract checker and make sure that everything's working nicely. So I made a language to do that called UBF, which is called Dynamic Session Types, which does all of that. And I didn't publicize it very well. I think I wrote a paper about it and then hoped people would find it. And then after about 10 years, nobody found it. So I think I posted a blog article about it or something. And then waited another 10 years. No, it's about 15 years old. People who use it swear by it, because it's actually very good. Right. So that was one of these messages, Describe the protocols. That's a first-class design document. It should be the top of your design documents. The RFCs that describe what's on the wire are the most important documents in your system. The APIs are, thank you. Right. The next lesson is well, RPCs, remote procedure calls, fail differently to procedure calls. It makes programming very easy to pretend that remote procedure calls and procedure calls are the same thing, but they fail completely differently. There are failure modes for remote procedure calls that local procedure calls don't have. So if you're kind of describing the world like that, we send a request to a remote system and we expect a response. What happens if this happens? Send a request and the thing crashes. Okay. Now, Martin had, I think, one page about failures in there. Well, I have a PhD thesis just on failures and written a couple of books on that, so I think you didn't actually do justice to this subject. It's actually slightly more complicated than a remote procedure call. So this is well, we have promises, right? A promise is a guarantee that you're going to give me something in the future. So instead, to parallelize computations, we use these things called promises. The trouble with promises is that people can break them. This is, what's that from? Casablanca, right, yes. So it's Humphrey Bogart and Ingrid Bergman, and he ditched her, basically, a few years back. So that's why she's looking pissed off, because the promise was broken. Okay, so distributed computing is the art of resolving broken promises. Okay, so how do we do that? Well, the telecoms people have been around a bit longer than the datacoms people, so they've figured out a rather nice way to do this, I think. The standard way of doing things is, well, it's okay to send a response back immediately. What you want to be guaranteed is you will get a quick response to your first message. That really just confirms that the server, or the person you're sending the message to, has received the message. So you have a kind of protocol like this. So for most things, you send a request, and you get an immediate confirmation back. There's no computation being performed here. It's just an acknowledgement that the server has got the message. Okay. And then sometime later, you get what's called an indicator. That tells you that the service has been completed. And so the specifications will tell you what this time is. And they'll also tell you what this time is. So the 3GPP specifications lay out in detail this. This is going to take 2 milliseconds. That might take a minute or 30 seconds or something like that. And then you know what to do. You know what's gone wrong. That's much better than just relying upon the fact that everything's quick and everything. And you can modify that idea a little bit. Like this, I think, if you're going to ask the question, I don't really know how long a remote process is going to take to do something. So when I send it a request, I might like to get an immediate answer back that says, OK, I got this message, and I think it's going to take 2 seconds to compute. And then I know that, well, if I've waited 2 seconds, that's fine, it comes back. But if I've waited 3 seconds here, I know it's an error. So I could do that dynamically if I wanted to. I think that might be a bit fun. The other thing is, a nice thing about these sort of protocols, it's nice to embed into them things like redirects at a very low level. Because then, I saw this first in the Microsoft Instant Messaging protocol. It was very nice, because you start off, and this is a instant messenger thing, and there's a global server. If you don't know anything at all, there's a global server in, I think it's around Robin DNS or something. It'll point you to one in Britain, or if you start in Britain. And it goes there, and you just send your IP address, and you haven't even sent a login, it will immediately send you a redirect. So redirect to this other address. And then you go to that one. Then you go with your name, sort of log in as Joe, and it'll immediately send you, it'll redirect like that. So it just bounces around the network. So you're doing the load balancing. You're not doing it in an expensive load balancer in front of the corporate data center. You are doing it at home. So, I mean, DNS works by, there's no load balancer back in the corporate thing. You've just got the addresses of several machines. One of them fails, you go to the next one. It's really easy. So these kind of self-repairing protocols, self-balancing protocols, very good. Like ARP is another one, the address resolution protocol. You know, when you're on a local Ethernet thing and you try and access a machine on that net, if you don't know the MAC address, it just broadcasts on the Ethernet and it says, where is this IP address reply to something? The MAC address is broadcast on the net, everybody listens, and it just self-repairs, so you can plug stuff in and out. And these protocols are very good. So I think you need to understand, the message from this is you need to understand that remote procedure calls fail differently to local procedure calls. And don't assume they're the same thing, they're completely different. The next thing I think I would suggest it's a good thing to do is handle errors out of band. This is kind of funny. Well, it's not funny at all, really. If you imagine a communication channel, a socket or something like that, you send a request down it, you imagine two types of things come back. You get a normal return, meaning the service has worked, or you get an error return, meaning the service hasn't worked. That's what I would call in-band error handling. You're handling it in the same communication channel. It's often really simplifies things if you have two channels. You send a message to the normal request channel, and then you send errors to the error channel, and only valid replies back on the normal channel. Just makes the logic a lot easier. And if you bake that into libraries, you get what in Erlang are called supervision trees, which I think Acker has used, and things like that. But basically, it is this notion of separation of normal case from error handling cases. That's the separate error channel. In this case, it's a tree. So instead of handling errors in the nodes themselves, you handle them one level higher in the tree, and then you separate them, and that becomes very nice. The next thing you should do if you are building distributed systems is you should avoid impedance mismatch. What's impedance mismatch? Well, when I was working at Tel, the managing director came and sat down next to me one day at lunch, and he said, Joe, he said, he said, people tell me that Erlang's jolly good. And you've built this big Erlang system, and they've built this big system in C++, and they tell me that's jolly good. So why can't you just sort of connect the two together, and then it'll be jolly good, he said. And he didn't know anything about computing. So I thought, well, Erlang's like Meccano. Do you know Meccano? Meccano's really nice. I used to build stuff with Meccano when I was a kid. It was great fun. So Erlang's like Meccano, and C++ is like Lego, and they're both jolly good. But a construction that was made sort of out of Meccano and Lego actually wouldn't be much good, because it's just a horrible mismatch. And that mismatch is the impedance mismatch between data. If you look at a lot of applications, they're sort of doing, you might have JavaScript and it's talking through a socket, sending JSON terms, and it's being parsed by PHP, and it's going into MySQL. And on every one of these links, there's a data representation change and there's a parsing change. These really hit you because the most expensive thing to do in a system is parsing. Squirting stuff out once you've got an abstract syntax tree is easy, but parsing it to get it in is just about the most expensive operation you normally do in a system. Because you actually have to look at every byte. You have to look at every single byte. There's no way out of that. And because people just use really stupid protocols like JSON and XML and things like that, then you have no alternative but to look at every single byte. I think this is funny. The low-level protocols in the mobile networks are using ASN1. We sweat blood over every bit. We really count single bits. We pack them together just to save this limited resource, this 200 megabits per second that you've all got to share. And what do people do? They run JSON on top of it. Here we are weighing those bits with scales of gold. And they just waste all our space. I mean, it's terrible. Right. Next lesson is distributed and non-distributed systems behave differently. This is kind of funny. There's literally trivial problems in one domain. A trivial problem in distributed computing can be a totally non-trivial problem in the other domain. So, for example, you can't reliably store data on one node because it might crash. You need two. I mean, it's impossible on one. It's not just difficult, it's impossible on one node. You've got two nodes, it's suddenly possible. So an impossible problem becomes a tangible problem. It's not an easy problem, it's a tangible problem. There are other problems like consistency. In a single node case, easy. It's really difficult in a distributed system. And I think your intuition will be wrong there. If you come from non-distributed systems and you think, well, that was easy in a non-distributed system, it can be bloody difficult in a distributed system. So it's good to use libraries and things like that that are being validated for that. And I think you should start distributed programming early rather than late. I gave a course in distributed and parallel programming at Stockholm University. I just finished it a couple of weeks ago, and I'm going to give it again in the fall, but I realized I'd made a mistake because it was only in the last lecture we did any distributed programming in the class. So I got all the pupils, they all had to bring their laptops, and they're all sitting there, and I said, okay, so I want to build a sort of swarm so you can all talk to each other. I did it in the last lecture, not the first lecture. And I taught them how to do distributed programming. And I couldn't give them homeworks on that, because they all do their homework at home by themselves. So they're not actually communicating with you. And I suggested that they might like to form groups of 3 or 4 and start doing this stuff. And they didn't. I thought they'd find it fun, but they didn't do it. So I'm going to put that in lesson 1, that we start interacting early rather than late. Because the first thing that happens when you build it, you'll find a firewall. It's nothing to do with theory, this. It's to do with how to get through the bloody firewall and all these things you didn't know existed that stop your programs from working. You have to sort of get to nitty-gritty stuff and figure out those things. The next thing you should do is not break the laws of physics. I used to be a physicist. Eric Mayer's talk, he said he used to be a mathematician or something, so he's very keen on the sort of mathematics of computation. Well, I used to be a physicist, so I'm very into the physics of computation. So I was saying, I was talking last night. I mean, as a physicist, it's lovely because you can talk about the limits to computation. So there's a nice example of the limits of computation. What's the most powerful 1 kilogram computer you can make? Well, if you put more and more components into a computer, of course, it will get denser and denser and denser because it's got more and more components. So the limit is a black hole. Right, so your ultimate laptop is a 1 kilogram black hole, and that will survive for 10 to the minus 12 of a second, evaporate through Hawkins radiation, and do 10 to the 50 computations. Right, so that's nice. The ultimate 1 kilogram laptop can do 10 to the 50 computations, which is pretty cool. And then the next one up is the whole universe is condensed into a black hole and is working as a computer. And that could do 10 to the 55 computations per second. So when I read this number in the Erlang manual, it said, Erlang make ref wraps around after, may wrap around, it didn't say does wrap around, it said may wrap around after 10 to the 87 calls. And then I calculated at 10 to the 55 operations per second, and then take time divided times the length times the known life of the universe, turned out that it would run for 10 to the 17 universes, and then wrap around. So I thought, I don't need to worry about that. But you see, the point is, unless you know your numbers, you're not going to get anywhere. Because what does that number mean? 10 to the 87 or whatever it was. Okay, so Brewster's cap theorem and things like that, they're actually consequences of the laws of physics. So this is where messages are not delivered, machines fail, message propagation takes time. Jonas's list of Peter Deutsch's, was it Peter Deutsch or the other Deutsch? Peter Deutsch's observations on the fallacies of distributed computing. He is doing no more than pointing out the laws of physics. These are laws of physics. Stuff takes time, light takes time to propagate. You never know how something is now. Of course, you know how it was the last time you got a message from it. But that's not how it is now. And we never know how it is now because the ray of light coming from it hasn't yet reached us. And we might have missed it anyway. And if we do miss it, we don't know, did the communication medium break down? Did the computer break down? We don't know what to do. So don't put assumptions about, please don't break the laws of physics. You can think it's right, you can think you can do consistent distributed data, but it violates all sorts of principles of causality, so don't do it. Scale up, not down. What do I mean by that? Well, what you shouldn't do is start with a one monolithic application and then sort of, we've got 2 users and 3 users and 4 users and scale it up architecturally. You should start with sort of, billions of users and scale it down. And you're not going to get the same architecture. If you make an address space that can handle all the people on the planet or something like that, and you start with that, and then you say, OK, now we've only got 20 users, it's going to go a bit less efficiently than the one that assumes, if you start with 1 user, 20 users, make a hash table. How big's a hash table? Well, it's enough for 20 users. Oh, we'll put 50 buckets in it, and then it breaks, and then, oh dear, we've got 45 people. What do we do? Oh, rewrite the hash table to one with 100, and I've seen that. I've had a company, and we used to go to. You visit these companies, and they go like they start a little web thing or whatever, and they get a few customers, and then they get more customers. They buy a Sun Enterprise server, and then they get more customers. They buy a bigger one, and they have a bigger one, and a bigger one, and then they bought the biggest Sun Enterprise server that money can buy, and they got more customers. Oh my God! And then you have to tell them, well, you need to re-architect your entire solution, and then they're very unhappy. So I mean. No, it's difficult because it's a different architecture. You can't just add more CPUs, or you need an architecture where you can add more CPUs to things. Another problem which is going to come up, how are we doing? Yes, my favourite subject is names. Names are one of these things that don't hit you in the face when you've got a non-distributed system. But when it becomes distributed and bigger and bigger and bigger, it becomes more and more of a problem. How do we name things? There's a quote somewhere says there are only 2 different difficult problems in computer science. One is naming things, the other is cache coherency. And this is the naming things problem. So suppose we got some data. Methuselah Winkle. It started off as, goodness, I haven't noticed that. The slide started off as Rip Van Winkle. I had to look up on the net how old he was, but I couldn't find it, so I found Methuselah instead. But I haven't edited out the Winkle bit. It's not Methuselah Winkle. It's Methuselah, and he was 969. So you've got this data somewhere, and you have to ask some very difficult questions about that. If I put it in a file, what's the file called? What's the directory called? And on what host do I store that file? Or if you put it in a database, it's the same, what's the name of the table, what's the name of the relationship, where is the database? There's 3 extraordinarily difficult questions to answer. I have terrible trouble with my file system. Once I've written something, I put it in a file, but I don't know what directory to put it in. Then I don't know what machine to put it on. Actually, nowadays, I've solved all of that because I put everything in the same directory on Dropbox and replicate it everywhere. So that's solved that. And I'm a great fan of putting everything in one directory because it actually solves the problem of deciding which directory to put it in. But I don't like the fact the files have got names because then I've got to choose a name. So the obvious thing to do is to use the sort of Git approach. So the Git approach, you don't have any names. What's the name of the file? Well, it's the SHA1 checksum of the content of the file. So if I want to, so what is the name of the file that I put the data, Methuselah 9? Well, I just pipe it into SHA-sum here, and that's the name of the file. Well, that's such a stupid name. I can stick them all in the same directory. I'm not going to look at those names. I'm going to have to index it later. So what's the name of the host I store it on? Oh, well, then I could just ask, OK, so I've got this hash, and find me a list of addresses. So what have we done here? Just combined a couple of simple ideas. Use content hashes as names instead of real names, and use DHTs for resource discovery. OK, so I about a month ago, I thought, hang on, that's must be called it's BitTorrent plus Git. Now, what would you call git torrent plus git? Git torrent! Yes, so this is git torrent. And I thought, I won't tell anybody. I'll form a website called git torrent and register the domain name. And I Googled git torrent, found 2 projects to build it already. So, shame. It's a very nice idea, actually, because if you think about it, if you give somebody a hash, that's a complete tree of data. It uniquely defines that data. But you also have to tell somebody where to find it. So you say, well, OK, I've got this hash, but where is it? Well, it's on GitHub, or it's somewhere else. But if you use a BitTorrent-like system, you don't have to tell people where it is. So you've made it more flexible. You've made it easier to use. And that, I believe, can be used to solve the version nightmare problem. Because if you consistently rename things, this is Erlang. I've just done an experiment here with Erlang. By consistently renaming things by their hashes. So if we've got a module foo that calls a module bar, that's like a tag in Git terms. So we could actually say, well, the SHA of the binary is that. That's the SHA of the foo code, and that's the SHA of the bar code. So it really means that. And we have a table here that meant that, well, foo on the 12th of June was that, and foo on the 25th of February was that. So we could have all versions concurrently living in the same namespace. Well, there's no namespace anymore. That does away with there are no names, there are only hashes. There are no namespaces. And because there are no namespaces, there are no namespace collisions. Right. So Erlang's got a design fault. When it was designed, you can have 2 versions of the same module. They have the same name, but they can do different things. And how long have I got? Oh, OK, that's fine. The reason for that was Erlang was designed in 1985, and we had 2 megabytes of memory. It was purely pragmatic. We could have 2 versions of the module, foo and another version of foo. And the system didn't get confused, because it ran one version until completion inside a process. When the process dies and you sort of call it again, it's going to take the second version. But we'd only have 2. But now we'd have, well, not an infinite number, but with gigabytes of memory, we could certainly have 7,000 versions floating around and garbage collect the old versions and have no namespace collisions, which would be very nice for software development. Right. Next, measure, don't guess. Please measure. Don't guess. And don't send questions to the Erlang mailing list. I've got a lot of data. How long will it take to do it? And it's, we're doing a lot of quick. Put a number. I've got kilobyte of data, 10,000 per second. Want to do this within 2 milliseconds. Then I can give answers to things. The next thing, this is the thing that people ever get wrong. It's the granularity of concurrency. Get the granularity of concurrency right. If you don't program in Erlang, that might not mean so much to you. But if you've got what's an example? Suppose you've got, you want to represent 3 lifts in a building. How many processes would you use? 3. You wouldn't use 6 or 5 or 2 or 9 or 23. Use 3, because you've got 10 floors. You have 13 processes, 1 per floor and 1 per lift. This is called physical modeling that Carl Hewitt said was a property of actors. If you're modeling physical systems, you just look and see what the real concurrences, map it one-to-one onto that, and it'll program just write itself right down the thing. Well, then you should use a decent concurrency model. I have opinions about concurrency models. So the first thing you have to say is, concurrent is not parallel. Right, that's the first thing. This is in my, I put this on my blog, because our coffee room at work has got two coffee machines. And I walked in one day, and there were 2 queues of people waiting for each of the coffee machines. And then the coffee machine broke. And I thought there were still 2 queues of people who were waiting for the 2 coffee. And then they realized, and they merged into one. And so it's 1 coffee machine. So I thought parallelism, that's 2 queues of people and 2 coffee machines. And concurrency is 2 queues of people and 1 coffee machine. So it is actually quite easy. So you can explain it to a 5-year-old. But not some computer scientists, actually. No, there was a Haskell guide who gave me a talk on parallel Haskell. I said, you're using the wrong word. It's not parallel, it's concurrent. He said, no, it's parallel. I said, no, it's concurrent. And we had this bit of an argument. I said, well, explain, pray, how it's going to be parallel on 1 CPU, because it can only do 1 fucking thing at a time. At which he conceded that I might have a point. So you can't get more parallelism out of it than you've got hyperthreads. But people think you can. So, that's a law of nature, actually. Right, so there's all sorts of weird concurrency ideas, like, it's rather difficult to say what concurrency, well, it's not difficult to say what it is, but it's, well, perhaps it is, because a lot of people are claiming concurrency, storing state in a database is not a concurrency model. That's crazy. You suspend, you take your entire state and you put it in the database and you go to sleep, and then you wake up and you pull it out of the database. And that's terrible because of this impedance mismatch, because the database is meant to store stuff for years. It's not meant to store stuff for a few milliseconds while it's sleeping. That's not a concurrency model. Concurrency is not parallel, as I pointed out. And callback hell is not concurrency. Okay? It's callback hell. And, it's horrible. There's nobody... no, I don't want to annoy people. I won't mention the name of... No. No, but it begins with an N. And asynchronous callbacks with everything in the main thread is not concurrency, actually. I've even seen people say it's an advantage that everything's in the main thread. Oh, they can communicate with each other quickly. Yeah, but what happens if they crash? Oh, we don't do that bit. What happens if they block? Oh, well, everything stops. What happens if one of them takes a hell of a long time and goes in infinite loop? Well, all the other ones stop. What happens when we take a lock? Then all the CPUs stop. That's not concurrency, right? And it's going to get worse. I'm just, when you've got the 1,000th core CPU and you pull the global lock thing, just think you'll stop 1,000 computers with one little instruction. Isn't that cool? So don't do it. No locks. Don't lock it. And mirror the concurrency in your problem. Well, the other thing is you should not. This is an old one. Don't Postel. This is called Postel's Making Matters Worse law. Postel said an implementation should be conservative in its sending behavior and liberal in its receiving behavior. That meant if you sent it rubbish and it didn't actually crash, it would carry on and not tell you. That was a good idea when Postel said, because it was only like one protocol, it was the post office protocol. It doesn't make sense when you've got 20 or 30 things daisy-chained together. You really want to stop bad data coming into the system and tell you downstream that you don't accept the data. Otherwise, errors will propagate into the system. You won't be able to find out what went wrong. And if you're debugging like 4 things downstream of where the real error occurred, and it's on a different computer, you're really screwed. Okay. So don't do that. No way. Fail early, fail fast, crash, no defensive programming, never accept faulty data, don't send faulty data, and don't make matters worse by accepting bad data and carrying on. Shouldn't do that. No. Oops, on. Crash. Crash. And handle the errors out of band. Very nice. That's how we do it all. Use universal encodings. Let's have a look here. This is RFC 821, which, if you go back, it's the first RFC to define, I think Postel was one of the authors. Mail, the SMTP, Simple Mail Transfer Protocol, it's a text protocol. Mail from something 250 OK, receipt to 250 OK. Oh my goodness, what a mess. Everybody followed the first one. Okay. So if we go 1,791 RFCs later, what do we find? Oh, get docs to host w accept. This is 200 OK. I mean, it's got the protocol in front. It used to be just 250 OK. I suppose it's a slight improvement. It's got a few characters in front of it. This is 1,791 protocols later. Every single one of those RFCs in between has got an ad hoc parser. Crazy. Absolutely madness. Use a generic format and a generic parser, i.e. universal protocol. Something like XML, Lisp, S expressions, JSON, UBF, any one of these things. But do not use these stupid...
Did you say JSON?
Yes. Well, it's better than ASCII, isn't it? I mean, that's not saying it's wonderful, but it is actually better than ASCII. And as for this argument, well, ASCII is really good because you can see what's on the line. What do you mean, see what's on the line? Can you see electrons bouncing up and down? No, of course you can't. You see what a program has decided to print out for you, right? So you can play tricks with this, and you can use it. It's great. Finally, what I'm going to say about this kind of... I was thinking... that functional programming, this non-shared memory movement, the non-mutable data, that's like a massive wave. It's like we can't avoid it. If you look at it from a distance, it's a tsunami that's moving like this. It's going to crash over you, whether you like it or not. You can't stop it from happening. You're like a little cork bobbing on the sea, sort of watching it. And you might, if you look, 5 years later, you'll be a little bit higher, and you'll be higher. You can't stop this stuff. So you might as well just sort of drop it, or don't use shared data. If you're using locks and mutexes and shared methods and things, it's going to go. It might not go tomorrow, but it's going to happen. This wave of complexity will hit you. And simultaneously, we're seeing, why are things changing? Software changes when hardware changes. If the hardware stays the same for many years, the software will stay the same for many years. Now, what's happened in the last 20 or 30 years is processing just got faster and faster, but that hasn't changed how we write. Well, it has changed how we write software. We write rubbish software today because, well, come on, if you've got a gigahertz clock or 3 gigahertz clock, you don't have to try hard, do you? I mean, and if you want your program to go faster, you just wait a few years. You wait 10 years, and it'll go 1,000 times faster. I mean, what's the bloody impatience? Who is so fucking impatient they can't wait 10 years for the program to go 10,000 times faster? It's really easy. The thing I said to years ago, I said to our research bosses at Ericsson, I said, look, what our job is to do is to write beautifully clean code, beautiful code, small, elegant code, try and prove that it's correct. And then we wait until the processor speed becomes so fast that we can just deliver that without any changes or transformations. And that's happening. We are moving downstream into this. So we've got this legacy LN code. We're just running it. It ran it on a 64-core processor. It went 33 times faster without tweaking. That's kind of cool. He who will win eventually will have clean and beautiful code they can maintain, because most of our costs are in maintenance. They're not in writing the bloody stuff in the first place. Okay. So what is driving these changes are, clock speeds went up, and then they hit this sort of chip speed of light boundary, physical boundary. I mean, the clock speed went up and up and up and up and up. The chips got bigger and bigger and bigger and bigger. And in 2004, you hit this limit where you couldn't reach a ray of light couldn't travel over the entire chip in one clock cycle. So the chip couldn't get bigger because you couldn't have a synchronous clock circuit where you clock everything, and you couldn't increase the clock rate. And at that point, you had to divide the chip in, 2 cores or 4 cores or quad cores. And now, for energy reasons, if you can drop the clock rate, the energy use goes like the square of the voltage. Drop it down to 500 megahertz or something like that. It's going to go fine. You're going to get a lot of benefit in energy terms. So for me, that's great news, because I used to, I'm brought up on less than 512K of memory and a 1.6 megahertz clock speed. So, all this gigabytes of memory and gigahertz clock rates, that makes lazy programmers. And in fact, it's made systems that just wouldn't work if it weren't for the amazingly fast clock speeds. And we built these horrible systems that nobody knows how they work or why they work. And when they fail, nobody knows where they failed. And so we kind of make random changes in them. We need to break systems down into small, understandable components with message passing between them and with contracts describing what's going on between them so we can understand them. Otherwise, we just won't be able to make software that works. I think that the limit of human understandability is something like 128 kilobytes of code in any language. So we really need to sort of box things down into small units of computation and formally verify them and put protocols in between. And that's going to happen because the next generation of network on chip, FPGAs and VLSI chips, haven't seen them yet, but things like 1,024 CPUs with a megabyte of memory on each core will be coming out this year, and they'll run at about 15 watts. They'll have 100 times the price performance or the power performance of a regular CPU. They're just so bloody powerful, we don't know what to use them for, but we do know how to program them. That's a nice thing. And we have to go back to these small memory models, pure message passing, no shared state. I mean, any sharing in this, any locking is going to be catastrophic. And we're going to see those coming in this year. By 2019, we should see a million cores on a single chip, and we're going to have to program those things. Right, so I think it's about time to finish, I suppose. Yeah, thank you.
Joe, thank you very much for that. That was really, really good.